Let me just simply introduce the people that I work with. I work with Omar Guerrero, who is one of my colleagues at the business school, and who's got a background in economics and computational social science, and also Robert Axtell, who is a very well-known person in the computational social science world for his work on Sugarscape, and he's been involved in the development of ideas of computational social science for a long time. So what I'm going to try and talk about today is this idea of modeling labor in a way that is high resolution, in a way that is as precise as we can, and very well fundamented in the use of data, so that we can try to go beyond some of the more accepted methods that are around, mainly because these accepted methods lose a lot of information. So I think this is quite an interesting way to go about things. Okay, so let me just get started. Okay, interesting. Let's see. It's a very special color. And this is a very special. Okay. Let's see. Yeah, it's not what I meant.
Slide that's invariant under that operation.
Yeah, that's right. There's a symmetry here. Parity operation. Yeah, I think we'll try to do something.
Yeah, no, except
No, you haven't, right? Let's try this again. Okay. Oh, it's closer. All right. Okay. So let me just give you a bit of framing, right? If you want to look at labor markets, you want to look at them. I mean, of course, you can look at different scales. The more interesting things, I suppose, and the things that involve policy are those that go up to what we would call the macro level. So something that you could consider to be macroeconomics, for instance. But really, we know that labor market starts from the ground up. So there are all of these people, all of these firms making decisions about who they hire, people making decisions about where they apply for jobs and so on, when they leave, and this and that. So it really is a micro to macro problem, right? And so in that sense, this transition has in spirit the same logic that you have in statistical physics. So economics has that approach, and in the context of macroeconomics, it's called micro foundations. And some people will know this a lot better than I do because I'm not an economist. So, and the way that it basically works is you've got micro level agents that are the microeconomic part of the problem, and then there's some sort of a set of rules and interactions, and then they lead to macro level behavior. Right? Now, once again, of course, the goal is to try and understand and predict what's happening at the macro level. And one of the problems that has existed in a lot of these contexts is that at the micro level, there are many situations in which the micro assumptions are not justified empirically. It's not always, but that happens quite a bit. And so it becomes a good choice to postulate some micro mechanisms that are consistent with the macro observations, but that in many cases have not been empirically tested. So, so then the idea in this case is go back to administrative data and try to construct labor dynamics from the ground up. So let me just say something very general. So this talk is basically about that microscopic model of job transitions, and to try and find an empirical network that reflects the dynamics of the system well. What we managed to do is actually present a good number of results that are both qualitative and quantitative in terms of the predictions that come out of this model. There's something very interesting in this, which is that with our models, we can connect two areas of economics that traditionally have not been talking to one another, which are the areas of firm size distributions and labor economics. And then, well, obviously we should care because this is employment, this is labor, but I guess it also gives us a new picture of how to understand the landscape of firms and what role it plays in labor. So, let me just give you a kind of a simplified version of how things look. So if you have a homogeneous model of labor dynamics, and that is, you know, the majority of the models look like this, and the ones that don't are simply tweaks on top of this. They look a little bit like this. So if you've got job search is a random process basically, and then that random process would look a little bit like this in these prevailing models. So you've got a bunch of employed individuals, unemployed, and you've got vacancies. And then what happens is, with some sort of probability, you get transitions. People going from being unemployed to occupying some vacancy. Others that are employed become unemployed, either voluntarily or they get fired or you know, whatever mechanism. And then maybe some other unemployed tries to get another vacancy and they fail for some reason. Maybe that vacancy is taken, maybe there's some other reason why it doesn't occur. But basically the treatment is you've got a probability, and it's a random process that you either achieve or fail at occupying that vacancy. And you know, somebody else tries and gets another vacancy. So these models are actually quite successful. They have given explanations that are qualitatively correct about why, for instance, you may have vacancies in the country, and you have unemployed people, but not all of the vacancies get occupied. So you can, if there is a probability to fail while you're unemployed trying to get a vacancy, and you know if that occurs, then of course you will have that not everybody that could be employed is employed. So that's you know, that's one of the good results. You can in fact make improvements on this because this of course is a very simplified picture. We know that if you're a plumber, you're not going to go and apply for a surgeon position, right? And that's a very simple way of understanding why there is some sort of a random process here. But you could improve this by making submarkets, right? You could say, well, there's a sort of a technology and there's a sort of services, okay? There are geographies that you could put in here, etc. So one thing is clear though, you are missing information about firms, and that is because actually these models are not based on firms. They're based on buckets of employed, unemployed vacancies. So then, and the firms are just a representative firm. And then when I say a representative firm, I mean the singular, right? So then the role of firms is ignored in these models. And then what happens is that a lot of countries, a lot of regions actually are dependent sometimes on one single company that if it goes down, it fails, then it takes out the whole local economy. So how many university towns do we know, right? How many, how many people here have heard about Nokia, for instance? So, you know, these examples are very simple examples. I come from Venezuela. The company there is the oil company. So that's a very essential element about employment. So we would like to recover that. And then actually, this is something more technical, but it's quite important. When the models are so averaged, one of the things that they have is a very fast convergence to equilibrium. So that means that if there are shocks of unemployment, the speed with which that propagates through the system is very fast because there's very little structure that can somehow moderate the way that the unemployed move around, basically. So, okay, so let's see what a slightly more complicated model would look like. Okay, so I would like to think of the data first. So if we start at the point of the data, then we can try to build a picture that relates to it. So this would be a set of employment records that we could use. And in fact, administrative data of this form exists, or forms that are equivalent to this. And what are we looking at here? So we're looking at a list of well-identified firms and people that work in those firms. And you can look at lists like this that track the system in time. This is on a yearly sampling rate, but you could have different things. And you know, here I'm thinking very much about data from Finland, which we have access to, and this is one of the things that I'll talk about. And what you can see here is, for instance, because the employees are identified, right? What happens is that you will see transitions of individuals going from one firm, so say employee 3 that used to work at firm 1 is now working at firm 3. And employee 4, which was working at firm 2, is now also working at firm 3. You can see the dynamics of this occurring, right? And you could continue to track this over time. And so, for instance, if you look at some of the data sets that we've gotten our hands on, so we look at data from Finland for 20 years, and basically this offers all of the companies that they can get their hands on, which is virtually everybody that is in the formal sector, and also all of the workers that they identify in those companies. So this is a pretty extensive data set. There will be collection error, but from the standpoint of Statistics Finland, this is basically complete data about the Finnish system. We have a sample from Mexico, which tracks individuals. So it tracks it the other way around. You got an individual, and then you have timestamps for when they stopped working somewhere and started working somewhere else. And it's tracked with specific days. So you could say that that's resolution with data with daily time resolution. And it tracks about 0.5% of all the workers in the formal sector in Mexico. So the sizes of the data set. So basically in Finland it picks up about 200,000 firms, and it picks up about 2 million workers. And in Mexico it picks up 200,000 firms and about 400,000 workers.
Just to understand whether you have certain metadata or whether you don't have it, do you only have, for example, firm ID 1, or do you also have a label that says this is from a certain industry? I'm just curious if you have any of those other things as well.
We have a bit. We are getting more, but we're not using it.
Okay. Okay.
It's a good point. And that's part of the development.
Okay, I'm just curious whether you have it.
Okay, so let's just think about one way that we could actually focus on this data, right? And if we think that firms are the important element here, because they are in fact the employers, then we could try to structure the information in the following way. So take a firm, place those individuals that are working in that firm, take all the firms and just sort of label them around like that, and place the individuals there. And we'll talk about the errors in a minute, right? So what you would see in the dynamics of the problem would look something like this. So an individual, say for instance, that guy right there, this individual decides that they're going to change jobs. So they go into some sort of say holding pattern, if you like. I'll get to that in a minute, but basically that means they're looking for a job, right? So they look around, and then they see other firms that potentially have vacancies, and they apply somewhere, and they get a job somewhere else, right? Okay, so make one jump like this, and we can, it's quite simple. We can always say that the employees belong to a firm, right? And I put these arrows down because what tends to happen, and I'll talk a little bit more about this in the next slide, what tends to happen is that if somebody makes one of these job transitions, social scientists know that actually the probability that another person will make the same job transition is higher than if you just pick somebody at random. And so then, or a destination at random rather. So then, tentatively, I'm thinking there are probably some sort of underlying relationships between these firms, right? So some other individual may try to make a transition, may try to make the same transition and not be able to. And we will keep track of these individuals. These individuals that somehow want to get out from that firm. So the unemployed, in fact, because of this idea, we will associate them with the last firm that they worked in. And this will become a little bit clearer in a second. So, okay, so let's just for a moment stop and think about what we've said. So we've got individuals working at firms, they are trying to change jobs, okay? So if there were no rules for these job changes, in other words, I'm working here, I could apply anywhere. I could go to work at a hospital as a surgeon, or I could go and pump gas at a petrol station, right? I could do all of that. Then there would be basically no structure in the movement of workers around. That doesn't sound right? So what would sound right? Well, you would guess that there are reasons why certain firms would see transitions between them and others not. So you could say, well, that may be an issue of categories and so on. Well, it turns out that we can always be proposing all of these reasons, and it would probably be best, instead of us giving it a label that we decide, we just let the data tell us which transitions really occur beyond what you would call a random expectation, right? So that's how we begin to approach this. And so what we say is, well, let's test statistically. If you have a firm, you got individuals that are coming into this firm, and we see that from the data. Other individuals are leaving the firm, right? An interesting thing to do would be to say, well, if we just allowed these transitions to just occur randomly, right, then how different would that be from our observations? So when we do that, basically, so we construct these statistical models where we indeed allow these firms, the transitions to be random, and we do many of them to create a null model. We calculate the expectations of seeing transitions between pairs of firms, and then we compare it with what we see. And it turns out that a great number of the transitions occur in a way that is non-random. Okay? So, yeah.
So, just to understand what you mean by randomness or by the random model, does it mean that every firm may be connected to any other firm by these edges randomly, or do you have some underlying structure on that?
So the structure
some
that,
sort of degree distribution that we assume or anything.
Yeah.
Any
so what we fix is the number of individuals coming into a firm and going out of a firm on the basis of the data. So we say, here's a firm. We know that between year n and year n plus 1, a certain number of individuals came into this firm and a certain number of individuals left the firm, right? We randomize that, okay, and then we see what the probability would be to see, say, one transition between this and that, and 2 or 3, so on. So we do the test on that basis, okay? So once we test for what we observe, we see actually that a lot of the jumps are not random. They seem to actually be significant from the statistical point of view. So, and these are large numbers of transitions. So basically, the total transitions are 800 or some thousand that we see, and that's quite a large number. So there are in fact a lot of events. So with this, we then think, okay, actually, it makes sense to construct networks of firms that are tracking all of those pairs that seem to be significant in terms of statistics, and then say, well, maybe on top of that as a structure, one could model the flow of workers, and that's our logic. So, how do we do this? Well, okay, I will sketch the math. I won't get into that. I have a couple of slides down there if we need to, but basically the idea will be the following. Okay, so we take the data, construct the networks that we consider are the significant networks, and then we do the following. We make a model in which an individual is walking around this network, okay? And so that walk is tracked in this way. The individual has a probability R sub I of working at firm I. The individual could have decided to change jobs. And so because the individual can only change jobs inside the network, it cannot be, it cannot just jump from anywhere to anywhere, right? When an individual may become unemployed, that individual will sit around its last employer, okay? And that is, again, because the only routes it has to change to another job are through the network, okay? And that is another probability that we track. We have some specification that tells us what the firms do, okay? The firms are open to receiving applicants with some probability per time step. So we track this in some, kind of a discrete clock. So time t, time t plus 1, and so on. At some random time t, a firm may decide to accept applications. Okay, that's what he tracks. Of the applicants that try to get in there, a fraction h sub I will be higher. And then on every single time step, and we take this from the data, employees may decide to make the transition between being employed to being unemployed. So basically to start looking for a job. And okay, and then just as almost like a spoken rule of what's happening, individuals will try to apply being at firm I to firm J with a probability that's given by the fact that firm J needs to be open, needs to be receiving applications. And then what they do is, because the neighborhood of firms, some of them may be open or closed at a given time step, and then the next time step may look different because these decisions are random, then the probability that they will apply from I to J for a job depends on also the possible configurations around them, and then one of the firms that is open is chosen at random. So if I have 10 firms that are connected in the network, at some time step 5 of them are open, I will pick one of them with a chance 1 in 5. Okay? And then ultimately what this looks like is, if I am employed at time t at firm I was one of the possibilities is that I was also employed at time t minus 1 and didn't leave, or that I was unemployed at one of the neighbors, applied and got accepted at I. The other possibility, the other thing that's happening is I become unemployed sitting at I. That means that I was either employed at I, previous time step, and I'm leaving, or that I was unemployed at I, tried to get another job, and couldn't get another job. So okay, so these are just the general rules. And so you can calculate this very precisely, and we focus first on the steady state, because actually the steady state can tell us a lot. Not only that, but in fact, I think we can justify that a lot of economies, a lot of the time, are in some sort of steady state. So we are not always either collapsing or we're not always in a complete boom. There is some regularity to what's going on in the background. So this is a histogram of the inflow minus outflow of workers measured on one of the data sets. This in particular is measured out of the Mexican data set. And basically it tells us that the probability that the inflow minus the outflow of a given firm is some value is actually very peaked around 0. So the majority of firms are not expanding massively or shrinking massively. Typically, they are staying at about the same size. Okay? So, yeah.
How exactly did you get rid of temporal dependency?
I mean, you look at different time windows, but normal. I mean, because if you look at to say you look at one day, the most likely thing that's going to happen is that that day,
Nothing
you know,
happens.
yeah, exactly. Either nothing happens or somebody left, so then it looks like everybody leaves and nobody comes in, right? So you have to look at some time window in order to allow that kind of steady behavior to occur, basically. So you get enough samples, I suppose. Okay, so you know that at least justifies it. It's worth looking at the steady state. I mean, you've set up the model anyway, so you wouldn't look at the steady state anyhow. But it matters basically. So so you look at the equation for, say, employment. Well, you look at all of them, and then we can actually find explicit solutions. So nice little compact things if we assume that all of the firms have the same kind of probability to be accepting applicants. Okay, we just make, this is one of the simplifications that I will talk about for quite a bit, which is all of the firms are equally likely to be opening for applicants. Now there's another reason why we take that, and that is it's very hard to get data on how often any given firm is open to receive applications. Because we don't have such data, it's reasonable to at least give a shot to the homogeneous model in that case. Okay, and so we solve this as a Markov chain, and we get these kinds of solutions. And these solutions, let me just talk you through them a little bit. The likelihood that this walker, this kind of representative worker that's moving around, is working at I in that steady state is proportional to the number of connections that firm I has, and then this is that rate of leaving the firm. Actually, 1 over that is the average time that individual spends at that firm. So in fact, what we are saying is that the probability that you are working at firm I is proportional to the number of connections of I and the average time that people spend working at I. It's quite sensible. It's also proportional to the acceptance rate of I. So if I is a firm that accepts with a lot of frequency, then yeah, why not? And it's also proportional to the average acceptance frequency of the neighbors of I. Because if the neighbors of I accept people, then it means that there's going to be more applicants to meet, right? And so that's what we're seeing here, and this is just a normalization constant. Let's make sure that the sum of all these probabilities gives you 1. Okay? Now, being unemployed at I, it's going to be related to being employed, because you first have to be employed there and then leave, right? And the only difference between these two expressions is that this rate now changes, and this is now so 1 over this quantity is the average time it takes you to get the next job. Okay? So let's see. And okay, I mean these are some technical points that I've already made. Right. So does this work? Okay. So my equation is was the probability that one individual is working at I. So if I have a workforce of H individuals, then I'm going to ask, what is the average number of individuals that are working at firm I? Okay, and if this is my workforce, then it turns out that this is going to be the average number of individuals working at this firm. So, from the previous equation, we would expect this to be proportional to the number of connections and the average time spent on a firm. And so I would like to look at the data, right? So I'll explain this red line in a second. So these are measured from the finished data. Here we're taking firm sizes, and we're taking the measured number of connections and that average time of employment. The way that you measure the average time of employment is you can do it in 2 ways. In the Mexican data, you can actually measure it directly. In the Finnish data, what you do is this probability to leave a firm, you can also calculate it in the following way. You can take the size of the firm and then the number of individuals that leave that firm in that year. And you can then do that for the 20 years, so the 20 samples that you have, and you can then come up with a value for that quantity. So all of these dots are measured, and then that red line actually comes from this analysis. So because of the dots, I don't know how frequent anything is, really. I mean, they're just on top of one another. This surface here is telling me the following. If I look at the probability that a firm will have size L sub I conditioned on this ratio, okay, then the most likely thing that can happen is that indeed the firm's size is proportional to this ratio, okay? And that's what this surface is telling me. And that red line that you were seeing is just simply this line. These dots here are the measured most probable relationship between L and this ratio K over line. So basically the interpretation of this is that indeed what we see in the data is that the firm sizes are proportional to those ratios. We also have this sort of kind of kooky idea of some firm-specific unemployment, right? Which always, will definitely bother you because you think, well, I'm unemployed, I'm not associated with any firm. But actually, the point is that the fact that I used to work somewhere says something about me. It says something about what I am naturally skilled to do, what my career record has done, so on and so forth. So my ability to get the next job does relate to where I used to work before, right? And that, and so then curiosity, does this actually do anything? We just take the results of the calculation, again with a workforce color age, and this is the ratio that we would expect to see. And this is again measured. This is the Mexican data where we can track this. And then this is the same sort of three-dimensional relationship. Now, it's not perfect towards the large sizes. It would be difficult to do that because actually we're just tracking individuals. So that means that we cannot, for instance, tell very well how large a firm is. If we were tracking firms and then the individuals inside of them, then we would have a better sense of what the size of the firm is. But here, we have that the fact that it's a sample of the data. But still, it's not too bad for about 3 orders of magnitude, which is pretty decent. So, the other thing that should happen is this. If I know the relationship between the firm size and K over lambda, then I should know something about the distribution of sizes of the firms, because that proportionality from the standpoint of probability means that I can calculate, if I know the distribution of one of those quantities, I can calculate the distribution of the other. And what should happen is that the two distributions should be parallel to one another. And so these are distributions of the firm sizes, and so that's the darker bluish color, and then the more light purple color corresponds to the connectivity. They are indeed parallel to one another. You could talk about the fact that that the average time that you spend on firms is also part of this. It turns out that when you relate these two things, the average time seems to be uncorrelated and roughly Gaussian. So for technical reasons, it means that only K and L need to be related. So that's quite interesting. And what it actually means is this: we're measuring a relationship between firms by the fact that they make transitions between one another, and that workers make transitions between them, and this is giving us a connectivity for each firm, and then that is somehow giving us an explanation for the sizes of firms. And so then, instead of us proposing some probabilistic model microscopically that leads to the distribution of firm sizes, we're measuring something and we're explaining distribution of firm sizes. That hasn't been done. So this is quite interesting. And then this would be a distribution of unemployment. This is Mason's favorite stuff here. There may be a power law in there.
No.
We don't know. We don't know. But we haven't looked at this quantity. It probably is something interesting because we would like to know if some particular firms are contributing to unemployment in some sort of disproportionate way, basically. And that's, I think, what's important about this quantity. Okay, we could talk about the labor simulator, actually, the thing that we use to illustrate that, because Tahan's developing a carpal tunnel. No, I'm kidding. We'll leave it for another time. We could do it in the break or something like that. But then, okay, and this is just simply to say, we can also do computational stuff with this, and so. If the model is more complicated, you put more parameters, or your parameters are very specific, something that you measured in a particular economy, and you don't need to apply it to all of the other economies, then you can do things like temporal analysis. So for instance, say that you tweak your model so that your unemployment rate changes at some point from this level to that level, and you tweak that with one way of doing it. So you change the opening rate, so how often are firms allowing people to apply. Right, so if you do that, you can then also make measurements of what the model would actually do, because there's a little time of adjustment, and then you can see the whole cloud of all the different possible histories of the different companies. You can do the same shock, but you can do it with now people leaving the firms at a different rate, and if you do that, then you get overshoots and things like that. So basically, even your equilibrium behavior you don't arrive at it in the same way. So that's so you got all kinds of possibilities with this. So okay, so just to say, basically, this model allows us to do some things that are quite interesting. We can go to a higher resolution, both of not space but firm space and time. You can actually do things that, if you are applying policy, right? Aggregate models can only tell you what you can do at the very top level. So you say, I'm going to address problems of the technology sector. But you can't really tell what you're doing inside of that technology sector, or how that technology sector's effects may knock on to other places. So this allows us to do that. It allows us to do it because of the resolution, but also because we can construct the models with data on the fly. You don't have to wait for a statistician to say, oh wait, what if it's geography plus weather? Okay, well then you have another model or whatever. You don't have to do that. It just happens from the data, right? As we have introduced these new ideas of using this firm network and this firm-specific unemployment. And then one of the things that's really interesting, I find very appealing, is connecting these two different areas of thinking about employment, thinking about firm sizes as one single interconnected piece. Okay. So I think it's got some interesting possibilities for policy. You can do a bunch of other things, and we are developing now in the direction of understanding the dynamics of the problem. So how long does it take for a shock to settle down, et cetera, et cetera. And I think it's a promising area. And here are some of the publications that are out or under construction, if you will. All right, thank you very much.